All right, so yesterday we left off talking about air columns after we had talked about standing waves. Okay, so remember that standing waves are not like what their name would imply. They don't stand still. Okay, but their pattern does because of repeating patterns of interference. Yeah. Okay, so the standing waves are the result of reflections and constant production of waves, and then they're going to produce these patterns of constructive interference and destructive interference that we call antinodes, the areas of constructive interference, and nodes, the areas of destructive interference. Okay? So what we're going to look at today is how does that get set up in the two different types of air columns. Okay? Closed air columns and open air columns. Right? And I forgot to get that thing ready, so I'm going to go do that right now. Okay? In case the buses don't run tomorrow, I did post last night the unit exam review for this unit. Okay? If the buses don't run tomorrow, look at that post. It's got a recording from last semester, or 2 semesters ago, whatever it was, okay, for this review, okay, and the review package. Okay? The review package is abnormally long. I don't know, I just found lots of stuff on waves, so okay, it's got a lot of stuff in it. Just look through it, watch the recording. Okay? If if the buses don't run and you can't get here, don't try. Okay, if it's minus 40 and the buses don't run, okay, then you shouldn't get on the road either. Okay, because if you break down, I wouldn't want something bad to happen to you. Okay, I'll post whatever is going to happen that day and you can watch it from home. All right, everybody got me there? Okay, because I just want you guys to be safe. If it's not safe for a professional bus driver to get you here, you with your inexperienced driving should probably also not attempt to get here. Okay, it is okay to not show up if the buses aren't running. Okay. All right. So I'm going to get the air column set up, which won't take me but a minute, and then I'll demo that. What we have here, guys, is a closed air column. Okay. It is closed because one end of it is water, which is a reflective surface. The waves will hit the water and they will reflect off of it and come back out. Okay. So air and waves can only get out one end of this column. Right. Now, it's going to vibrate or resonate at different frequencies. Okay? And those frequencies obviously have different wavelengths. So this thing is going to resonate at different points as I lengthen the tube. Okay, so all I'm going to do is pull that inner tube further up, and because it's got measurements on it, I'll be able to tell what the length of the resonating tube is, and from there, I'll be able to figure out what the speed of sound is in this room. Okay, because I'll be able to measure two things. The frequency, because it's written on my tuning fork, okay, and the wavelength, because I'll know how long the tube is. Okay, everybody kind of follow me there? All right, so the first thing we're going to do is look for the first resonant point, which according to this diagram is going to have how many wavelengths in it? 1/4, right? That's 1/4 of a wavelength. So the first time I hear a loud sound, okay, on this tuning fork or in this tube, I'll know that's where I'm at. Hear it there? Okay. Can someone read the measurements? Because I can't hold the tuning fork and read the measurements from. Tell me where the water level is.
20.
Exactly 20?
Exactly 20.
Okay. So our first resonant point, okay, is at 0.20 meters. All right, so that's when there's 1/4 of a wavelength in the tube. Okay, according to this set of diagrams, the next time I get a resonant point, how many wavelengths should be in the tube? Okay, this was the one I just found. It was 1/4. The next one is going to be 3/4. So if this one was 20, the next time I hear a sound, it should be 60. Right? It should be 3 times that. I should be able to predict where the next resonant point is going to be. All right. What's it read, Rob? 58. That's not too bad. That's pretty close given, the kind of hokey equipment we're using here. Okay? So 58, we'll go with 0.58. Okay, next resonant point should be 5/4. Okay, this was 1/4, this is 3/4, this is a full wavelength plus another quarter. Okay, so if this was 20, this one's 60, okay, or sorry, this one's 20, this one's 80, the next one should be at 110, or just at 100, right? If 1/4 of a wavelength was 20, 5/4 of a wavelength should be exactly a meter, would you agree? Okay.
Like 98.5.
Oh, 98.5. I love it when things work. But they always work because I teach physics, the science that always works. Okay. 98. All right, so here's how we're going to use that to calculate the speed of sound in this room. So this is why we do this as a demo and not a lab anymore. All of these leak really badly. And what a lot of people would do, because there's just a rubber stopper in the bottom of this tube, people would put them up on the desk for some reason. And then when they would lift them up at the end of the lab, the rubber stopper would come out. Where do you get wet? I don't know how many times we have people who look like they wet their pants when we were doing this lab because the rubber stopper would come out and get them right here. Yeah, I'm careful not to get that. Okay, put you in the corner. You need to go over there. Okay, watch yourself up here, it's slippery. All right, so now, if I know that this length here was 0.20 meters, and that's 1/4 of a wavelength. What's one wavelength? Okay, this is 1/4 of a wavelength. One wavelength is 4 times longer than that, yes? So what's 4 times 0.2? 0.8, right? So according to this, my wavelength should be 0.80 meters. Okay, that's where this formula comes from. This is the fundamental right here. Okay, the first frequency, okay, or the first wavelength that I get that resonating at. 4 times the length of that tube gives me the wavelength. At this one, okay, this is 3/4 of a wavelength. So 3/4 times lambda equaled 0.58 meters. Okay, so if I want to find the wavelength, I just divide both sides by 3/4. Okay, I get 0.77. That's pretty close to 0.8. That's 0.773, right? Yeah. Okay, meters. And then for this one, which was 5/4 of a wavelength, that equaled 0.98 meters. Okay, so if I divide 0.98 by 5/4, I should get the wavelength. Okay, 0.784. Are we getting around the same number for all of these? For the wavelength, is it pretty close? Okay, that's pretty close. Right? So this sound, because I use the same tuning fork, should I get the same wavelength every time I calculate it if it's the same tuning fork? Should be. Okay. So now that I've got those numbers, I'll just average them to get our average wavelength. Okay, so we'll go plus. Oh, and then plus 0.8. The other one. All right, so our average wavelength there is 0.786 meters. Okay, so now I know the wavelength. Okay, the frequency of the tuning fork I used was 440 hertz. Okay, band people, what note is that? Nobody ever knows the answer. I wouldn't know either, except that it's carved onto the tuning fork. A, apparently, is the 440 hertz. Okay, so if I want to calculate the speed, I just have to go F times lambda, agreed? Okay. What should I get about for a number? speed of sound in air in this room should be 340, maybe a little less than that, okay, something along those lines. Okay, so F 400 time, or sorry, 440, not 400. Okay, 440 times 0.7, what did we say? It was 786. It's not too bad. 345 meters per second is the speed of sound in air in this room. Okay, given the temperature in this room and our higher altitude, that sort of makes sense. Okay, should be around that. Okay, everyone follow what I did. Okay, now, here's the thing we got to realize. As I was moving that tuning fork up, did the volume of the sound change? Right? Like when I found the construct the antinodes, it was definitely louder, right? Were there any points where it was really quiet? Yeah. Okay? And they would be evenly spaced between the resonant points. We'll do this again. There's still some water left in here. Getting pretty good puddle over there. Okay, so as I raise this up, listen for the changes in volume. You can actually detect where I hit a node as well. Oh, I missed it. That makes it louder. Okay, can you hear where the nodes are? Okay, it gets noticeably quieter. Take a chunk of it. Okay, as I pass those points. Okay, now the thing with closed air columns is that they only resonate at odd numbered frequencies. Okay, they only resonate at F1, F3. F5, F7, and so on and so on. Okay, any harmonic that is an odd number, I'll get that loud antinode at. Okay, anywhere that's quiet is where I've got an antinode, or sorry, where I've got a node at the top. Okay, so the first place where I get a loud sound, the waveform looks like this, and that's F1. This is F3. What's the shape of the wave in that tube at F2? What's at the top? Yeah, a node. Okay, because 1/4 of a wavelength away from this is a node. Okay, so this was 1/4 of a wavelength. This is half a wavelength. But at half a wavelength, I've got a node at the top, so I don't hear anything. It doesn't resonate. Okay, then if I go another 1/4 of a wavelength, I get another antinode at F3. But at F4, I have a node at the top again. I'll have a full wavelength in the tube, but I won't hear anything. Okay, is that sort of making sense? So the limitation of a closed air column is that it only resonates at every other harmonic. It can't resonate at the even numbers because there's a node at the top. Okay? This is the advantage that an open air column, as a musical instrument, has over a closed air column. An open air column resonates at every frequency. Okay? Because its reflection is not off an end, it's off the inside of the tube. So it makes a wider range of sounds. Okay, everybody with me so far? All right, so here's the kind of thing I would ask you about a closed air column on a test. Okay, I would give you some situation where you would have to decide whether the situation was an open air column or a closed air column. Okay, and then I would say this column is resonating at its fundamental frequency, and the tube is this long, and the speed of sound is this many meters per second. What's the length of the tube? Okay, and you would have to work backwards, find the wavelength, find the length of the tube, or I'd give you the length of the tube, ask you to calculate the speed of sound like I did today. Okay, something along those lines. All right, we'll do a few examples, but that's what I'm generally going to be looking for. Okay, so that's closed air columns. Okay, now can't demonstrate with an open one because they just don't work very well. Okay. So open air columns, as their name would imply, are open at both ends. Okay, since they're open at both ends, there's nothing at the ends for it to reflect off of, so it reflects off the inside of the tube. Okay, and we get this waveform as our fundamental frequency, our fundamental wave. Okay, how many wavelengths are in the tube here? Okay, in the closed air column I had this much. That was 1/4. How much is this? 1/2. Yeah. There's half a wavelength in the tube at the fundamental frequency for an open air column. That's why the formula for an open air column isn't lambda equals 4L, it's lambda equals 2L, because lambda would be twice the length of the tube. There's half a wavelength in it. Okay? Now, with open air columns, you always get resonance. F1, F2, F3, F4, it doesn't ever skip any. Okay? So the next time there's a resonant point, it's another half a wavelength away. Okay? Next resonant point, half a wavelength away. Okay? 1, 2, 3. Okay? We just keep going up. So this is half a wavelength. This is a full wavelength. This is a wavelength and a half. Okay? Because here's a wavelength. There's a quarter. There's a quarter. So 1.5 wavelengths. Okay? This is 2 full wavelengths. Okay? Because you got a full wavelength here. Okay? 3/4 and 1/4. Okay? Here you got 3 full wavelengths. Okay? And so on and so on. Okay? Everybody all right with that? Okay. All right. So our waveforms, as we said, look like this. Fundamental frequency, okay, it's half the wavelength, or the tube length is half the wavelength. At the next one, it's a full wavelength, and so on and so on. All right. Let's have a look at some examples here, just so you kind of get what we're looking at. Okay, try this one. So you've got a closed air column, right? So right away, because it's a closed air column, we know that lambda equals 4L. As soon as you see closed, that's the formula you're going to use. Okay, and it's telling you it's resonating with a fundamental frequency of 256 hertz. It gives you the speed of sound and wants you to calculate, okay, the length of the tube. Right? So what you have to remember is, what's the shape of the wave for its fundamental frequency for a closed air column? Okay. Okay. They want you to find the length of the tube. Okay, give you a few minutes on that one. Write it down, and give you a few minutes, then we'll walk through it together. Okay, so on this one, we know we have a closed air column. They want us to find the length of that column. Because it's a closed air column, the wavelength is equal to 4 times the length of the tube. Can I calculate the wavelength already? I can, because I have the speed and I have the frequency. Okay, so I can go V equals F times lambda and manipulate that for lambda. Okay, so V will equal, or sorry, lambda will equal V over F. So that'll be 343 divided by 256. Okay, so that's going to give me the wavelength. 343 divided by 256. All right, so the, whoop, not divided, not just times. 343 divided by 256. Okay, so the wavelength of that sound is 1.34 meters approximately. Okay, so now that I know the wavelength, I can calculate the length of the tube by simply dividing the wavelength by 4. Because I know at the fundamental frequency, there's only 1/4 of a wavelength in the tube. Okay, so I take that number, divide it by 4, okay, and I got 0.335, okay, actually, yeah, 3.35 times 10 to the minus 1 meters for the length of the tube. Okay, everybody with me there? So really, as long as you understand like fundamental frequency stuff, you're good. Now, here's a way I might kind of alter that question slightly. Okay? I might ask you if that's if 256 hertz is F1, what's the next frequency you would hear out of this tube? Remember how yesterday we said each frequency is a multiple of the first? Right? So what I've got there, the 256, that's F1. What's the next frequency I would hear?
768.
768. Because the next frequency I hear is F3. Okay? Remember, closed air columns don't make noise at even numbered frequencies. Okay? And that, I can trick a lot of people with that. Okay? Because they'll go, oh yeah, well F2 is the next frequency, and so it's 2 times this number. Okay? Not thinking that, oh right, those air columns only resonate at 1, 3, 5, 7. Okay, the next frequency out here would be 3 times that number. If it was an open air column, it would be F2, it would be 2 times that number. Okay. All right, I want you to write this one down. This is an open air column. Okay, so basically it's like the same question except, oh, that's bad luck. I should really change the numbers in that question. Okay, try that one anyway. Okay, you have an open air column resonating at its fundamental frequency of 256 hertz again. Okay, and we want to find the length of the tube for this one. Okay. Now remember, because it's an open air column, that's the waveform that's in the tube at its fundamental. Lambda equals 2L for an open air column. So does this one work very similar to the last one we did? Only thing that's different is we use lambda equals 2L. Okay? Everything else is the same. So I've got to calculate the wavelength using V over F because I know those two numbers. 341 divided by 256. Okay? So that'll give me my wavelength. And 341 divided by 256. Okay, gives me 1.33. And if I divide that by 2, okay, I get 0.6660 okay, meters for the length of the tube. Okay, for that length there. Okay, now there's all kinds of different ways I can ask those questions. Okay, sometimes I might ask you calculate the speed of sound and then apply it to something else. Okay, or I might give you the air temperature. And then you'd have to calculate the speed of sound from that 332 plus 0.6 T and then go into the air column question. Okay? Because all air column questions essentially work the same. Okay? You're either using 4L for a closed air column or you're using 2L for an open air column. Okay? But otherwise, they work all pretty much the same. So, what I would like you to do is in your digital workbook here, okay, there are closed air column questions and open air column questions. The first 7 are all closed, and then 8 to the end are open. So what I'd like you to do, we've done 1 and 8. Okay, so I'd like you to just alternate. Do 2, then do 9. Do 3, then do 10. Okay, and we'll just go over them together as we need to. Okay, so have at those ones, guys, and we'll go through any that give us trouble.